Yeah.
Yes.
All right, perfect.
Okay.
Okay, cool.
Is it recording?
Okay.
Yes, it's recording.
Yeah.
Okay, bet.
Okay, so with module 13 deals with Lewis structures, like where the electrons are in a molecule or an atom, how they bond and what works with them. So if you remember, they're represented by dots. So like for example, we'll go with sodium. And the Lewis dot structure tells us like how many valence electrons there are. So who can tell me how many valence electrons are in sodium?
1.
So we would just put one dot as so. So if we were to go to, so in case again, if you were wondering like why it's one, you could just look at your periodic table and look at them by group. So group ones, they have one valence electron. Group two has two. Skip the transition metals because they're weird. Then group three starting with boron, be 3 valence electrons, and carbon with 4, 5 on the group 5, 6 on group 6, 7 on group 7, and then your noble gases with helium all the way down, they have a full set of 8 valence electrons, and that's the max you can have. So going on to say magnesium, we have 2. So much like how you draw your arrows one by one, the same thing you would do with your valence electron. So with magnesium be 1, 2. So who can tell me how can I do it for carbon right now?
6.
6 valence electrons for carbon?
Oh,
No, it's for your valence electron.
There's 4.
Carbon has 4.
Yes, and someone said in chat, I put 1 on each side. Yeah, it's correct. So since it has 4 valence electrons, going 1, 2, 3, and 4. And so on the rest. So like once you fill up each side, you start putting them in pairs. So let's go with chlorine, right? How many valence electrons are in chlorine?
7.
So let's start counting them up, doing it. It'll be 1, 2, 3, 4. All sides have 1, so now let's pair them up. 2, 5, 6, then 7. So exactly, 1 will be left unpaired. So this is just ground state chlorine, just as the atom by itself. So the way we connect this to bonding, let me show you guys real quick. Where start off with ionic bonds. So who can tell me what happens to electrons in an ionic bond?
They move from the metal to the non-metal.
Exactly. So let me see someone in chat. Exactly, they get transferred. So let's do sodium chloride, so NaCl, right? So we've seen the Lewis dot structure for sodium. So here's our dot, and as well as for chloride, right? So if you think about it like this, it's much easier if you remember your trends of like electron affinity, electronegativity, and all that. Since chlorine is more electronegative, it'll really pull away that electron from sodium. But at the same time, it's much easier to get rid of 1 electron than it is to get rid of all 7 in order to kind of fill up its valence shell. So what happens here is sodium will give its electron to chlorine, and then what happens?
Na turns into Na plus, right?
Exactly. So we have Na plus with no electron, well, no valence electrons to be more specific. It does have its outer shells, but we're just looking at its outer shell. And then chlorine here becomes negative, so because it has an extra electron, which I'll draw right here. So if it'll load for me. So yeah, like kind of like, so just like this. So this is what we do with ionic bonds. Same thing, say we were to look at magnesium chloride, where you need 2 chlorides in order to work it out, right? So let me fix this up. So here we have magnesium, and let's put 2 chlorides on each side, right? We know the Lewis dot structure for magnesium. I'm going to put 2 dots on 2 sides here just to make it simpler. And the 7 valence electrons for chlorine. So here, if you remember, since if magnesium were to lose both of its electrons, it becomes +2, right? And since chlorine is naturally a -1, whenever you turn it to ions, it would need 2 chloride ions in order to balance out the +2 magnesium. And this is why, where the electrons get transferred over equally. And then we'd be left with our magnesium +2 with our chloride ions as a -1 here. Are there any questions so far? Is anyone kind of lost? All right, I'll take that silence as a no. So this is the basics for your ionic bonding here. where one gets smaller, becomes positive, while the others get negative because they gain those electrons. So now that we, oh, sorry, I didn't mean to do that. So now that we have ionic bonding out of the way, let's focus on covalent bonding. And what happens to electrons when you bond covalently?
They
They share electrons.
electrons.
Exactly. So when they share electrons, they're sharing a pair of electrons, two electrons at the same time. So let's look at water. Let's look at H2O. So how many valence electrons are in oxygen?
6.
So let's count them up. So it'll be 1, 2, 3, 4, 5, 6. And how many valence electrons are in hydrogens, for example?
1.
1.
Just the one. So let's just write the one like right here. So, so since they're both nonmetals and they need to bond covalently, they need to, like, in order to complete their shell, they need to share electrons, right? So what you would do, so for right here, we can move electrons anywhere we want, just so you guys know, they don't have to be strictly on a certain side. So let's move this pair down here at the bottom, and let's move the little lone electron here. So since they need another electron to complete their shell or to become satisfied, they would just share, you would form a line between those two. And this line would signify 2 electrons. So whenever you see a molecule, you see like a line or a double line like this, just know that each line means a pair of electrons. So now in total, technically, oxygen has 8 electrons in total because there's the pair here, another pair, and then these 2 lines representing pairs as well. In this case, hydrogen has 2 electrons where it has 1 line connected, so it has 2 electrons in its outer shell now. Is everyone clear? Anyone have any other questions? All right. Oh, see someone in the chat.
They just said no questions.
Oh, no questions? Oh, okay. Thank you, Soya. So, okay, so moving forward. So, if you guys remember, who can tell me what the octet rule is? Because this is very important for covalent bondings.
Doesn't that include the CNOF, like the carbon, nitrogen, oxygen, and fluorine?
Yes, so carbon, nitrogen, oxygen, and fluorine. But what of these 4 atoms or elements? Like what does it mean when they have to follow the octet rule?
I think they're supposed to have 8 electrons.
They're supposed to have 8 outer electrons. Good job.
Yeah.
Exactly. So whenever you're bonding with like your Lewis structures, it's very important that whenever you're dealing with these elements, that they must have like 8 electrons in its outer shell. So let's take, for example, carbon dioxide here. So let's say we have carbon and dioxide, so our 2 oxygens, since we know our valence structure for them. Just quickly fast-handed this. So do any of these elements need to follow the octet rule?
Yes.
Which ones?
Carbon and oxygen.
Carbon and oxygen.
Exactly. So since they need to have an outer shell of 8 electrons, and we can do so by having them share pairs by bonding them with each other, let's focus on the right oxygen right here. How can I get this to a full 8 electrons?
We put a double bond to carbon.
Line.
Exactly, a double bond, a line, perfect. So let's connect this line here where it has, since it's a pair, this is 2, this other pair 4, 6, and 7. And someone mentioned a double bond, so we can just move this bottom electron up here alongside, and we can move another electron from carbon to be alongside it, and then bond it together. So now this oxygen has 2, 4, 6, and 8 electrons in its outer shell. So this oxygen completes the octet rule. So let's focus on the other oxygen. What do we do with it now?
It does the same thing.
Exactly. Oh, sorry, were you continuing? Sorry, I didn't mean to cut you off.
No, yeah, I mean, it does the same thing with the previous oxygen atom.
Yeah, exactly. So we get another double bond here. So let me just bring the other pair here. So we bond those together, and we see we have 2, 4, 6, and 8. So that completes the octet for that oxygen. Now, is carbon completing the octet right now?
No.
Is it?
Wait.
So let's count them. So we have a line here, which is a pair. So that's 2.
Oh, yeah, it does. It's my bad.
Yeah, that's okay. So we have 2, 4, 6, and 8. So now we have all of our atoms that need to follow the octet rule following the octet rule. So if I can just let me just clean this up real quick. So this would be the Lewis structure for carbon dioxide now, like lone pairs included all. Now, in the event that you get tired of putting dots, it's okay to just put lines like this as lone pairs. Because, you know, if you can associate a line becoming a pair, you can write it out like this. So like a little something to like keep in mind in case like you get tired of writing dots. So
Oh,
with that,
wait.
oh, you have you have a question?
Yeah, so the lone pairs are the pairs that are not like shared with other electrons, right?
Exactly, yes.
Oh, okay.
Because remember back from electron configuration that electrons like to be in pairs. So that's why we write them this way. So let's,
Thank you.
you're welcome. So let's work on another example of, let's say, what kind of molecule should I do? Any ideas, Sophia, of a molecule?
Should we jump into exceptions or should we still keep it easy?
Let's keep, oh, someone have a question?
Nitrate. You could do nitrate. Nitrate's a pretty like one
Yeah.
that is
Okay,
typically
so
confused with.
okay, so if we're gonna go into polyatomic ions, I feel we should, let's cover formal charge right now. So is everyone good on the octet rule, these elements and how they work and all?
Yes.
Yes?
Yes.
Okay, perfect. So let me quickly erase this. So what, who can remember or tell me what is formal charge? All right, so put it shortly, formal charge, what it is, it's identifying the individual charge of an atom within a molecule. And that kind of tells us whether the molecule is neutral or the whole molecule as a whole has a charge. So let's go back to our example of carbon dioxide, where the way we would count it. So let me quickly change color here. So the way we would calculate it is we would take the number of valence electrons that it's supposed to have. So as the atom by itself, so supposed to, subtracted by the number of valence electrons that it currently has in molecule. So in molecule. And what do I mean by that? So a short way of doing this is that you can draw a box around the atom, including its lone pairs and whatever lines it's connected to. So whenever you come across a line when drawing your box, you draw the line in between its bonds, like so. So since we cut the bonds in half, those electrons would like be counted as one instead of a pair now, since we're only including what's inside the box. So to start off with the formal charge for carbon, how many valence electrons carbon have by itself? Like, is it supposed to have as an atom?
4.
Or
So it would have 4. And how many electrons are within its box here?
isn't it 8?
8?
Remember, now that we put this box around, we only count what's inside the box. Since we cut the lines in half, that's technically one
So-
electron.
Yeah, so it's 4.
Yeah, 4. So we subtract 4 minus 4, we get 0. So the carbon here is neutral. So we get a formal charge of 0 for carbon. Now, what about, since both of these oxygens are the same, we can just do 1. So if I draw this box around here, how many electrons is carbon supposed to have naturally?
6.
6.
And how many are present within the box?
8.
6.
6, because we cut the lines in half right here, so they would count as 1. And here we have 2, 4, and then these 2, 6. So that would make it 0. So we know that this oxygen has a formal charge of 0, which means since this oxygen is the same, we could also say 0. So in total, the total charge of the entire molecule would then be 0. So it'd be neutral, because that's how carbon dioxide is. So following that, let's work on your polyatomic anions, which you work back with solubility, your nitrates, your carbonates, sulfates, phosphates. And some of you may have wondered, like, why do they have charges? And this is the reason why. So let's start off with nitrate. So NO3, and who can remember what was the charge of nitrate?
Just -1.
-1, right? So right now, let's write down the elements that, would take up the Lewis structure. So we have nitrogen and then 3 oxygens. So just write it out like this. But before I kind of get into it, how many valence electrons does nitrogen have?
5.
And since we have 3 oxygens, how many valence electrons does oxygen have?
6.
6.
6, right? So the reason I'm trying to count up the total number of electrons is to that way it's represented in our Lewis structure. Since it has a charge of -1, we had to account for that extra electron. So we would have +1 electron.
+1.
So how many total
4.
electrons? Oh, sorry,
24.
24. So we know that we need 24 total electrons within our molecule. So for now, let's put in our Lewis dot structure. Since there's 5 in nitrogen, we have 1, 2, 3, 4, 5. Our 6 in oxygen. And then, oops, let me fix that. So do any of these elements need to follow the octet rule first? Actually, before that, let's count our electrons here. So we have 2, like our total number of electrons. We have 2, 4, 6, then 12, then 18, counting all the oxygens, then 20, 21, 22, and 23. So we're missing 1 electron, right? So where would you guys want to put that extra electron? Let's say we put it here in oxygen. Let's put on this right oxygen here. So we have a total number of 24 electrons. So now that all of our electrons are accounted for, we need to make sure that something like the elements we have need to follow the octet rule. So do currently any of these elements follow the octet rule?
No.
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 All right. Does nitrogen need to follow it?
Yes.
Yeah.
All right, perfect. So how can I bond nitrogens and oxygens in order for them to follow the octet rule?
You could put a single bond between the nitrogen and each oxygen.
So let's do that. We make a single bond here, there, and over there. So we have 2, 4, 6, and 8. So nitrogen now follows the octet rule. Let's check the oxygens now. So we have 2, 4, 6, and 8. So our right oxygen does follow the octet rule. What about this bottom one down here?
Yeah, I think it does too.
Well, remember, we have 2, so this is a pair, so it'll be 2, 4, 6, and then this 7 right here.
Oh yeah, that was my bad.
That's okay. So it doesn't seem to follow it. Let's see. Oh, let me get rid of that line. So, wait. Yeah, okay. So, and then this one right here is the same thing, right? So we have 2, 4, 6, and then 7 here. So what do you suggest happens here?
I think the 2 pairs that are like on the top of nitrogen, they share with the 2 oxygens, right?
So let's try that out here. So let's bring that 1 electron down here, and then the other one to the side. Remember to keep track of your electrons when you're erasing them because you might get lost. And let me bring this. Oh, sorry about that. So let me bring this little lone pair here, right here. And let's make a double bond now for between these 2 in order for them to make the octet. So right now, do the oxygens now follow the octet?
Yes.
But what about nitrogen now?
One is missing.
Yeah, 1 is missing for nitrogen.
Really?
I don't think nitrogen is.
No,
Yeah,
yes,
no,
they're,
it
they're
should.
Nitrogen
I
has too
think-
many.
Too many.
Exactly.
I think nitrogen has 2 another extra pair.
So what do you suggest we do? And Sophia and Andre, you can like hop in anytime as well.
We'll just remove one of the double bonds.
All right, so let's remove one of these double bonds. So we have 1 lone oxygen and another lone oxygen here.
Or you suggest putting the other 2 electrons you just removed.
So
Anybody have suggestions?
Isn't this the one where instead of counting bonds, we count half of the bond? Or am I going crazy?
not yet, that's formal charge. This is
Yeah.
like following the octet, like how much they have in total for bonding.
Or...
Well, no, yeah. So he has those 2 dots. He erased the line. So what do you think he needs to do with those 2 dots right there? On the on the oxygen going downwards. So there are 2 dots now. So if nitrogen can't have another bond, where can those 2 dots go?
They go to the oxygen.
So let's do that. So we move that here. So let's put them on the side of it since this side, this front, eraser. Since this top side is already a bit heavy. Let me replace that bond here. So let's put them here. So does this top nitrogen and the bottom oxygen follow the octet rule now?
Yes.
Yes, it should.
Perfect. So here are 2, 4, 6, 8, 2, 4, 6, 8. Perfect. Now we have that. So what's next is to find the formal charges of all the atoms here. So let's focus on the right oxygen right here. Oh, if I can draw the little box. So remember, it's the number of valence electrons that it's supposed to have in the lone atom minus the electrons it currently has in the box. So how many valence electrons is oxygen supposed to have?
6,
And how many does it have currently within this box?
7.
So it has 7. So that gives us -1, which means this oxygen has a formal charge of -1. So this would, not 0, -1. So we have that down. What about this oxygen down here?
Well, it's I think it's the same, right?
Since it follows like the same structure as this oxygen, it would also be -1. And what about our final oxygen on the left side?
That would be 6 minus 8, I believe. Wait, 2.
Remember, we're not counting
No.
these as pairs anymore since the,
Oh, I mean
the
the-
box. Yeah,
No,
since the
it'll
box
actually be 6 minus 6, so that gives us 0.
Exactly, because we're not counting these as pairs since the line crosses them out. We're only
6?
counting inside them. Yeah. So it'd be since it's supposed to have 6 valence electrons, and since we cut these bonds in half within the box, they count as 1 electron now. So we have 2, 4, and then 5, 6. So yes. So 6 minus 6, 0. So this oxygen on the left has a formal charge of 0 now. So this would be 0. Now, what about nitrogen? So let me quickly draw the little box around it. How many valence electrons is it supposed to have?
5,
And how many does it currently have within the box?
4.
4, right? So that gives us a positive 1. So that would leave us with a formal charge for nitrogen as positive 1. So now we need to know what the overall charge is. And the way you would do so is now you. So what you would do is you have to add all of our formal charges together. So here we have positive 1 plus -1 plus -1 plus 0. And what overall charge does that give me?
-1.
Exactly. So now that we have the overall charge, the way you would denote it in here without having all this cluttered formal charges, let's just erase those. And what you would do is that you would draw like massive brackets around the molecule. And at the top right corner, you'll put its charge as so. And this will be your answer in finding the Lewis structure for like your polyatomic anions. Are there any questions so far? Anything confusing? Nope. All right. So let's go over another example here.
I was wondering if I could do one real quick, just maybe phosphate, if I could do that one.
Oh yeah, of course. Here, let me just clear this out. Yeah, I was thinking of doing phosphate as well. Here, let me just clear this out. So let me stop sharing. All right.
All right. Thank you. Okay, so yeah, another example that is another like exception kind of a little is the phosphate, right? The phosphate ion. So does everybody already actually, just real quick, does everybody know how phosphate looks like already? This is like a little recap of module 2. Can anybody tell me what phosphate is?
It's PO4 and with the -1 charge.
It's a -3 charge.
Yeah.
-3 charge,
Negative
yes.
3.
Okay. So that's phosphate, yeah. So this is, yeah, we're still gonna do a little bit of formal charge and also just different, we're gonna see how, because this was a good example. I wanted to do this one because this happened kind of in my workshop, which I wanted to bring up. So there could be different ways to write this, but I'm gonna show you here why formal charge is very important as to choosing which one is your most accurate one, okay? So usually you want to choose the one with like the Lewis dot structure. You want to choose it where your central atom has the least formal charge, like the lowest formal charge. Sometimes it could be 0 completely, so you choose that one. So let's do phosphate real quick with that being said. So it all depends on how you like to do your Lewis dot structures. So there was 2 ways that a student brought up. So there was one way that a student did this, okay? So she wrote her phosphorus in the center, and then she put all her oxygens on the sides, right? It's gonna have 4. So for starters, well, we can count how many valence electrons you're gonna have. So how many does phosphorus have?
5.
5, right? And then oxygen is 6, right? And then there's 4. And then am I missing one more thing?
Yeah, you need to
-3
account for the
charge.
-3.
3, right? Yeah, exactly. Okay, so 3, and that's going to give me a total of what? 32, I'd say. Anybody can double check that. Correct me if I'm wrong, but I think it should be 32.
Yeah, that's a 32.
So it all depends on how you like to start doing it. Some people like to write all the valence electrons out first. Some people just like to write their bonds already right away. And then, well, oxygen has to follow the octet rule, right? So then what they proceed to do on from there is write their all their octet rule filled out. So you know that each oxygen has to follow the octet rule. So let's count them up. So technically, if we did this right, we should have 32 valence electrons used up. So can anybody count them up? So it's 6 right here and then 2 right here. So it's 8, and you know it's the same for all of these. So 8, 8, 8, 8. How much is that? 8 times 4?
32.
32, right? So this one, technically this one's not wrong, but it's not the best option. And maybe if you've done the phosphate Lewis dot structure, you've gotten this, because that's what my student got one time, and she wasn't wrong, but it's just not the best option. And let me explain why. So let's do it another way now. So now let's do it where, let's say you do want to write all your valence electrons out first instead of making all your bonds. So let's write the phosphorus again, and then let's write all our oxygens. So now, and then right now we can actually do the formal charge to even prove this, okay? So how many valence electrons does phosphorus have?
5.
5, right? So 1, 2, 3, 4, 5, right? And then all the oxygens have 6, right? So it could be like that. Just make sure, I know I'm writing 2 dots at the same time. Just remember that technically that's not the rule. It's supposed to be like that, but just once you've done these enough, you already know where how many dots oxygen's gonna have. So you can just plan that out, okay? So if you see right there, well, you can already form bonds, well, right here. Right, we can already form at least one bond, right? Okay, so wait, hold on. I don't know why that happened. So you can form one right there, one right there. And then, well, this one, since it has 2, and you see that it has 2 right here, well, let's erase this one real quick. Let's bring it down. And let's have it over here, and it can form one double bond, right? So now let's count up real quick how many electrons we've used up, okay? So can anybody count them up for me real quick and tell me how many we've used up? Did anybody count them up already? I just want to be sure. Because I already counted them, but I just want to make sure someone agrees with me. So
I got 29.
29. Yeah, I got 29 as well. Yeah. Did anybody else get 29 just to have a third person
Yes,
check?
29. My mic wasn't working.
Okay, 29. Awesome. All right. So let's do 32 minus 29. How much is that? 3, right? So we have 3 electrons left, but let's do something real quick. So does this oxygen follow the octet rule? Yes, right? 2, 4, 6, 8. But these oxygens, if you notice, they don't, right? Because they still have, so it's 2, 4, 6, 7, 2, 4, 6, 7, and all that. But what about phosphorus? Does phosphorus, the fact that it has 10, does it matter? Or can anybody tell me why it does or it doesn't?
It doesn't matter
Because?
because it's not part of the octet rule.
Yeah, phosphorus and sulfur are an exception. They can hold more than 8. They're comfortable with holding more than 8. So, well, you see that this one's already following the octet rule, and you see that you have 3 electrons left. So what can you do with those 3 electrons to have a complete octet rule for all the other oxygens? So let me put this in I'm sorry?
No, you have to add the 3 extra electrons to each of the oxygens that.
Exactly, right? So I'm going to put it in a different color just so you guys can see. So we had 3 left, and we already followed the octet rule for this one. Well, we can add 1 right here, 1 right here, and then 1 right here because we had 3 electrons left. Now, if you were to count them again, we'd have 32. So now you're like, so now I bet you're thinking like, wait a minute, so which one would I choose? So this is where the formal charge is important. So let's find the formal charge of the central phosphorus in this one, and let's find the formal charge in the central phosphorus in this one. So remember, like I said, it's the one that has the least charge, like the smallest charge. So let's do that. Okay, so Alan, you were using a different equation. I use a different one, but I don't want to use mine because I feel like it'll cause maybe confusion just having 2 equations. So can you do yours for that one? Because I just, yeah, I don't know.
No, yes. So, because like I found it very simple, just because like, is it the one where it's like half of something equaling?
Yeah, I do
that
the
one?
non-bonding. So yeah, I do valence minus non-bonding and then like bonding divided by 2 or something. Yeah.
Yeah, this one I found much easier where if you take the number of valence electrons in the atom, so like what the atom is supposed to have, and you subtract it from the number of valence electrons that are in the molecule of the atom. So what I mean by that, like back in my example, so you would draw a box around the atom, you're trying to find the formal charge. So in this case, yeah, we're finding that.
Oh, okay. And then I count these?
Yes, since we drew a line in the middle of the bonds, whatever's inside the box would be counted as 1 electron if it's
okay,
one of those bonds.
So it'd be 5 minus 4 then, right?
Mhm.
Okay, yeah, it's I use a different equation, yeah, and I just didn't want to. I wanted to avoid that for the review. So yeah, 5 minus 4, so it'd be what? Plus 1, right? So the formal charge of the central phosphorus in this case is plus 1. So now let's do. We can find the rest of the oxygen, and we'll get the -3. But let's just find these real quick. Let's find the one for the other. Let's find the one for the other phosphorus. So we said that that one was plus 1. And phosphorus, well, let's do 5 minus, let's draw that box around again. So it's 1, 2, 3, 4, and 5, right? So it's 5. So that phosphorus has a formal charge of 0. So with that being said, what I told you guys that you prefer to use the one with the smallest formal charge. Which one would you think is the more accurate one, the more accurate Lewis dot structure for phosphate? This one, the one on the left, or the one on the right?
The one on the right.
Yeah, the one on the right would be your most preferred one or accurate one, okay? And real quick, does anybody know what would the difference? So like if I were to, let's say if these double bonds were right over here, like on my right side, and the electron, I just moved it over here, would that be Oh, okay, yeah, never mind. I'm trying to introduce resonance structures, but I feel like that wasn't a good way to do it.
I think what Andre's trying to say is, if we put the double bond somewhere else around the phosphorus, does that change the fact that it's phosphate?
No.
No,
I'm
right?
not.
Because
I
you
love
still
it.
have the same number of electrons and you still have the same charge on phosphorus.
Yeah, and then Andre gave that a name. Did anybody catch it? What is it called when you can move the double bond around and you still have the same element? I heard it.
Isn't it the resonance
Yeah,
structures?
the resonance. So if it asks you for resonance structures, lucky you, how many other phosphate diagrams do you get to draw?
4.
Yeah, well, 4 total, right? So
Yeah.
3 other ones, but 4 total, yes.
Yeah. So yeah, just that, because yeah, when that student of mine brought this up, technically she wasn't wrong, but it's just this is the more precise way. So technically, like when you do these things in real life, like when you see phosphate, like the more common one in real life, it'll be this one. Okay. So yeah, just know that. And if you see anyways, your charge for, you added 1 electron here. So you know that when you do when you do the what's it called, formal charge, you'll know that these oxygens will be -1 because you put that one there, that what's it called, that one electron. So you know that when you add them up, it'll be -3. So it'll be the most accurate phosphate one. Okay. So yeah.
Also, I kind of wanted to add, in case like you're trying to look something up, you're trying to look for the resonance structure for phosphate. It might tell you that the left one is also resonance structure, but that's a thing with organic chemistry. So yeah, watch out for that. So just focus on what you're taught in lecture. And if you see something different, then I guess you can just come talk to us if you feel like you need help. Don't worry about it. Just be careful whenever you try to like look something up, because technically the left side is a resonance structure, but that's not Gen Chem. That's something else.
Yeah. No, yeah, I just did this one because I mean, if someone did it, I feel like maybe someone else anywhere can also like do it as well. And I just want to avoid that error, you know? But yeah. Okay, so I'm gonna clear it.
I have a tiny trick to help with formal charges. If you guys are okay with me sharing that with you, or if you would rather just, keep living your best life. What do you guys think?
How does everyone feel actually on formal charges? Do you guys feel?
Yeah.
Or does it
Do you
feel a
guys
little
feel good, or do you want like share it? Okay, bet. You guys get confused. No, just kidding. Okay, so oh wow, the notes from earlier saved. Okay, anyway. So this is from way back in the day, back in my day. Just kidding. When I took Chem 1, I took it with Dr. Alexander. So he gave us these tricks. I thought they were fun, and they still help me. So I thought they would be fun to share with you guys. So formal charge, we said, is when we either add or take away electrons from an element, right? So the two tricks that I have are for oxygen and nitrogen. Okay, I don't have them for everyone. I'm sorry. Okay, so oxygen. How many electrons does oxygen usually have? Valence electrons is what I mean.
6.
6, right? So you have 1, 2, 3, 4, 5, 6, right? Okay, and then, but if it were to have a full valence shell, how many electrons would it have?
8.
8, right? So then because we added 2 electrons, what is the formal charge for this oxygen?
-2.
-2, right? So we know that if we have an electron, if we have an oxygen with 8 electrons, right, that has a -2 formal charge. Yes?
Yes.
Yes.
Okay, now let's say that we have an oxygen with a single bond, right? Single bonded to whatever, let's call it X. How many electrons would it still usually have?
6, right? Or
6, yeah, because that's how many valence electrons it usually has, right? Actually, let me draw this in a different color. Okay, and then if we make a single bond to X, right? How many electrons did we technically add to it?
1.
1, right? So what is the formal charge for this?
-1.
-1, right? So every time that you see a single bonded oxygen, it's going to have a -1 charge. Yes? So that's how you know that, if you have single bonded oxygens, those are going to have formal charges, and you're going to have to either make a double bond to get rid of it, right? Or fix it otherwise to try to balance out the charge. Yes? And then the last thing that oxygen can make, because it has 6 valence electrons, right, is it can make a double bond, right? So when we make a double bond to X, right, how many electrons did we technically add here?
2.
2, right? But because they are in bonds,
Oh,
do
that's
they add a charge? The answer is no, by the way. So when you see a double bonded oxygen, this double bonded oxygen does not have a charge because it's stable because it has all 8 electrons. Yes?
Sophia, aren't you supposed to erase then one of the pairs, one of the lone pairs? Because then it would be counted.
Oh yes, that's why it's not working. My bad. I'm sorry. Thank you, Andre. Yes,
No.
so you would have 6 electrons, right? And then you share 2. So then how many would you have total here?
8.
8, right? So because they're shared, they're not actually contributing to the charge on the oxygen, right? So this oxygen has a formal charge of 0. Yes? You should also know that oxygen doesn't have to double bond to the same thing. It can also have a double bond to two different things. I mean, two different things because this could be a carbon and this could be a carbon, right? But yeah, so this could be like X1 and X2. So this oxygen has no charge and this oxygen has no charge. And every time you see a single bonded oxygen, it's always going to have a -1 charge. And every time you see an oxygen with a full, by itself, with a full valence shell, it's going to have a -2 charge. Yes?
Yes.
Okay, awesome. The other one I have for is nitrogen. So nitrogen, I think we discussed it. Nitrogen likes to keep a lone pair to itself, right? So yeah, it likes having bonds or whatever, but it really likes to keep a lone pair to itself because it's weird like that. So nitrogen always keeps a lone pair to itself. But how many valence electrons does it usually have?
5.
5.
5, right? So how many bonds can it make if it keeps a pair? I see the chat, but I don't know what it says.
They say 3.
3, yeah, exactly. So you can make 3 bonds and still keep a pair, right? So when nitrogen has 3 bonds and keeps a pair, the formal charge is 0. Okay, can anybody think of a compound that has 3 of it bonded to nitrogen that we've seen before?
Nitrate.
Sure, but nitrate has a formal charge, so something with no formal charge.
I'll say this, it's in a lot of our cleaning products.
Yeah.
Ammonia?
Yeah, ammonia, NH3, right? Now, does anybody know of one of ammonia's friends that looks similar to ammonia, except it has 4 bonds to nitrogen?
Ammonium.
Ammonium,
It's ammonia's
right?
brother.
Yes, but what kind of charge does ammonium have?
Has a +1.
A +1 charge, right? Why is that? I'll give you a hint.
There's an additional hydrogen.
Yeah, so nitrogen likes to keep a lone pair, right? So when it gives that away to that hydrogen, it's salty. So what does it do? It keeps a positive outlook on life. Okay, anyway, that was a bad joke. I'm sorry. But you should also know that nitrogen doesn't have to make, it likes to make 3 bonds total, right? But it doesn't have to be 3 different things. It could be nitrogen double bonded to something and single bonded to something, or nitrogen triple bonded to something with its lone pair, right? Does anybody know of a really fun triple bonded nitrogen compound? Alan's laughing. Anybody?
Nitrogen. Nitrogen with nitrogen. So and 2.
Sure, yeah, that's one. That wasn't the fun one I was thinking of, but yeah, that's one. Alan, you want to tell us the one that you're thinking of?
Cyanide.
Yeah, cyanide. What's cyanide, guys? Do you guys know?
It's C and N.
Yeah, C and N, and it's triple bonded carbon. Okay, cyanide is a fun compound. Don't drink it for fun. But yeah, that was
I bet it kills you.
Yeah, don't drink it. Any questions about this? I know it's not super extra helpful, but it's just like, for me, I'm a visual person, so like I see single bonded oxygen and I already know I'm gonna have a formal charge, right? And then nitrogen is just helpful to remember the difference between ammonia and ammonium. Any questions, comments, concerns, panic, confusion? What does the chat say?
No questions.
No questions. Awesome. Okay, I hope you also don't have comments, concerns, panic, or confusion. I'm gonna stop sharing now.
All right, so we're in the last hour, so we're gonna go over module 14. Do any of you guys want to, or because I have the, let's see, because I have my what's it called, that class response open for OChem where they can see like the 3D space of it, like how it actually works.
Okay, let me stop recording and then we'll do that.
Yeah.